This is a conversation with Matthew Kleban. He's a theoretical physicist, notable for his work on string theory and theoretical cosmology. He's a professor of physics and the chair of the Department of Physics at New York University. In this conversation, we discuss his journey getting into physics, quantum mechanics, what is the standard model of particle physics. We also talk about string theory, multiverses, and the Big Bang. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, or rate 5 stars on Apple Podcasts. This project takes a lot of my time, money, and efforts. If you'd like to see it continue, do consider making a donation on Patreon, Anchor, or Instagram. If not through monetary channels, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For the forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now, it's no time. Ernest Rutherford had once said that all science is either physics or stamp collecting. In previous interviews, you have often said that you got into physics by accident. Mm-hmm. You wanted to be a biologist and then a writer. Mm-hmm. But in university, you ended up falling deeper and deeper in love with physics and maths. For someone who's often described himself as a skeptic at heart, what was it about physics that drew you in the first place and continues to draw you in today?
That's a great question. I mean, stamp collecting is actually pretty interesting as well. But what was it about physics? I think physics sits in between mathematics, which is this sort of beautiful but crystalline and kind of static structure. It sits between mathematics and more soft sciences like biology or chemistry, which are much more phenomenological and experimental. Mm-hmm. And it's a sweet spot, I think, because it lets us apply really powerful quantitative ideas that come out of mathematics to the physical world in a way that's really productive and has been extremely surprising in how powerful that's turned out to be. And I think there's a sort of a siren call of the theory of everything.
Yeah.
No one knows if we're ever going to get there, right? But it seems like we're making progress and in a very unexpectedly successful way. And so it's not crazy to think that we might actually be uncovering the fundamental rules that the universe obeys. It's also not crazy to think that it's not what we're doing and we're seeing some, outer layer of an onion and there's maybe infinitely many of those layers. So we don't know, but it's a really interesting thing to delve into. And questions about the origin of the universe, the fundamental structure of matter, the nature of time, the ultimate future. I just find these more interesting than really any other questions that we can ask. So that's what pulled me in ultimately.
Let's expand that even further. Let's linger on that. You described your relationship with physics. It's a very interesting relationship. It's in a sweet spot. And every day you're getting closer and closer towards finding out the truth in nature. Isaac Newton had once said that, I do not know what I may appear to the world, but to myself, I seem to have been only like a boy playing on the seashore, diverting myself in now, and then finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me. How do you view the work that you do? Is it just another 9-to-5 job? Is it something bigger than that? Are you chasing something bigger? Is there a bigger purpose to it? Are you ever overwhelmed by the work you're doing and the implications of it? Are you ever afraid of the fact that one day you might get closer and closer to the truth in nature?
It's definitely not a 9-to-5 job.
Okay.
That's just a fact. It's I wouldn't say, every waking hour, but it's something I think about at all hours. And that's because it's so interesting. It's hard not to. It's just a really fun thing to think about in your head. So especially when you have a new idea or when you're deep in some calculation and you're trying to figure out if an idea makes sense or not and what it predicts, I'm constantly thinking about it really at some level. So yeah, no, it's too interesting not to think about. It's just, it's a fascinating topic. So, I mean, I think really we don't know, are we, so sometimes people make this analogy to fish, right? So physicists. So if you're a fish and you're swimming in the ocean and maybe you're a fish that lives pretty deep down, to you, the universe is water. And the laws of physics are the laws of water, right? So there's a preferred rest frame where you don't feel any pressure from water rushing past you. There's a speed of sound in water, which maybe you can use to communicate. Maybe you have to be a whale, not a fish. But anyway, there's a speed of sound in water. And it's a very different world. It doesn't look much like what we think are the fundamental laws of physics, right? We like to talk about what are the laws of physics in a perfectly controlled laboratory where you're out in empty space? And in that case, there is no preferred rest frame. Physics is the same whether you're moving or you're not moving. So you can't tell if you're moving. It's only relative motion that matters. It's completely different than what this physicist would infer. But we still don't actually know, is that really the fundamental laws of physics, or is that just the layer that we can access now? And so in a sense, that's the most interesting question in all of this. And if we drill down deep enough, maybe we'll find out. And does that keep me awake or worry me that we might get close? I mean, that's really what motivates me. I think, why else are we here if not to discover new knowledge? I think there's intrinsic value in a lot of things, creating works of art. But a lot of it boils down to doing something new, something that has not already been done, and discovering knowledge that no one knew before. That is really, to me, the most interesting thing that we could be doing. I mean, that's my own personal view. So it doesn't frighten me. It motivates me. It's what I want to do. I want to leave a mark, where I've learned something that no one knew before, and hopefully it'll be useful. But ultimately, what I care about is not so much whether it's useful, but is it true? Is it really taking us closer to understanding the world as it is?
Finding something that no one knew before. Let's dive into it. Let's start talking science. There's two big theories that I want to cover with you today. The first is the theory of the small, where we'll move inward. We'll try to break matter down into smaller and smaller pieces until we breach quantum physics and string theory. And then the second big theory that I want to cover with you is the theory of the large. So we're going to move outward beyond Earth, beyond the solar system, beyond the galaxy, until we breach multiverses. Once we've covered both theories, we're going to bring them together, which many physicists have tried and failed to do, but hopefully we can bring it together. If not in a theory of everything, then at least in an episode of everything. So this is going to be a momentous event in human history. Are you ready?
I'm ready. Bring it on.
You're ready. Bring it on. Let's do it. First, let's start with the standard model of particle physics. Let's take an object. Let's take this block, for example. What is it made of? If you break it down into smaller and smaller pieces, from molecules to atoms to electrons to quarks, at each stage, as you break it down to smaller pieces, what do you see?
Right. So it's made out of some form of plastic, which is a polymer. It's a molecule that's a long chain of hydrocarbons mostly. And if you look down into that, you could look with a powerful enough microscope and you would see, I suppose, I don't know exactly how they're arranged, maybe randomly, but you'd see a sort of spaghetti swirl of these polymers. You zoom in on those and you'll see the structure of a hydrocarbon, chains of carbons with hydrogens attached. You zoom in on those atoms and you'll see that there's a nucleus, which in the case of hydrogen is particularly elemental. But there's a nucleus which contains protons and maybe neutrons, and with a probability cloud of electrons, what people used to describe as electrons orbiting around the nucleus like a planet around the sun. Now we know from quantum mechanics, despite the fact that that is still taught to children in schools to this day, but what we know now is that
It's all a lie.
it was all a lie. It's not like a planet orbiting the sun. You can convince yourself of that immediately just from the fact that if it was, the electron would radiate electromagnetic radiation and fall into the nucleus in a tiny fraction of a second. So it cannot be that, and it's not. It's a quantum mechanical wave function where the electron is it's in a state where it has a probability of being somewhere near the nucleus. But not in any particular orbit. So now if you want to go further, as far as we know, electrons are fundamental particles. We've never seen any substructure in them. But protons and neutrons, those definitely have a substructure. So if you zoom in now on this nucleus and down onto one of those baryons, onto the proton or the neutron, you'll see that it's composed of 3 quarks. Those are smaller subatomic particles with fractional charges. And so the theory of quarks dates back to the 60s, and it was confirmed experimentally more recently than that, but by particle accelerators that smash protons together, for instance. So we're quite sure that there are quarks inside protons and neutrons. If you go inside quarks, again, it's like an electron. We don't know that there's any substructure to those. There might be, and I think most physicists would tell you there has to be, and I tend to agree, but we don't know for sure what it is. So that's as far as we've gotten in terms of confirm, let's say, theories that we're quite confident of and that have been experimentally well tested. And beyond that, it's more speculative. But happy to go there too.
I think you've left a lot of doors open for me. I'm going to quickly start exploring all of them. First, let's start with what you spoke about, the probability cloud for electrons, and they're not a fixed orbit. Such a lie that I was taught in high school. This is the perfect point to introduce quantum physics. What is quantum physics?
So quantum physics is the most successful theory in the history of human thought. That's what it really is. I think there's no doubt in my mind that that statement is true. And I don't think it's emphasized enough. It's incredibly successful because it explains phenomena all the way from what we were just discussing, electrons around protons, to the source of energy of the sun, which prior to quantum mechanics was a big mystery, to nuclear power and nuclear weapons, to the origin of structure in the universe. Where did galaxies come from in the first place? To the fact that if you take a cheap fluorescent light, it makes you look a little bit ill. And if you send that light through a diffraction grating or just take a CD or a DVD and reflect the light off it, you'll see that it's not a perfect rainbow. It's got only certain colors in it. So that's because the molecules in the gas are emitting only certain frequencies of light. All these things are consequences of quantum mechanics. And as you can see, they're on completely different scales and completely different regimes of the physical world. But they're extremely easy to understand and explain and make very precise predictions about with quantum mechanics. So it's very, very successful.
Let's define some of the terms in quantum physics.
Sure, yeah.
What is the wave function? What is entanglement? What is the uncertainty principle?
Okay, all right. Well, let's start with quantum. So quantum means discrete in the sense of not continuous, right? So, and it's called that because many quantities, not all, but many quantities in quantum mechanics are discrete. So one of them are, one such example, it would be the set of energies allowed for an electron that's bound to a proton. So in a hydrogen atom, the electron can't have any energy it wants. It has to have a certain discrete set of energies, at least up to some point. If you give it enough energy, it'll ionize. It'll become disassociated from the proton and fly off freely. At that point, its energy isn't quantized. But if it's going to be bound to the proton, certain energies are allowed. So that's the quantum in quantum mechanics. It's important to say not everything is quantized, even in quantum mechanics. For instance, the energy of the electron after it's ionized, not quantized. It can have any energy. Okay. So that's quantum. Now, what is a wave function? The wave function is the description of the state of the system you're talking about. So it's called a wave function because in quantum mechanics, there are phenomena that look a lot like interference of waves. And mathematically, it is a sort of a wave. And when you add together two waves, physically, if you shine light along two paths and then bring them back together, you'll see an interference pattern. Or if you think of waves on a beach, if there's a rock or something, or a wall with some openings in it, waves will come out of those openings or around the rock, run into each other, and you'll see a kind of a pattern of waves crossing each other. It's an interference pattern. So it's called a wave function because quantum mechanical states behave in that way. They interfere. Interference. Now, what else did you ask?
Entanglement and uncertainty.
Yes, thank you. All right. So entanglement is a tricky concept, but an absolutely fascinating one. I would start in the following way. So imagine that you have a green ball and a red ball. You have two friends, Alice and Bob, and you tell Alice and Bob that you're going to mail each of them one of these two balls. And the way you're going to do that is you're going to flip a coin. If you get heads, you send Alice the red ball, and if you get tails, you send her the other ball. Okay, so now you package it. You do this. You flip the coin. You package up the balls. You send them off. And Alice and Bob live very, very far apart. One at the South Pole, one at the North Pole. They don't have any internet. They have to communicate by carrier pigeon, which takes weeks. Okay, but as soon as Alice opens her box and sees that she has the red ball, she knows what color Bob has, even though there's been no time for her to talk to Bob. So that's an example of gaining information about something very far away instantaneously. And there's nothing weird about it. It's the fact that she was able to gain that information is related to the fact that she knew what the setup was. She knew that you were going to do this and that you did that in the past. So instantaneous transfer of information sounds odd, especially to a physicist, because Einstein taught us that information cannot propagate faster than light. But in this case, it didn't. The information really originated with you in the past when you told Alice and Bob what you were going to do. And so what happened is that Alice's state of knowledge collapsed down to one possibility. And in that possibility, she knew the color of the ball that Bob received. Okay, so that's a kind of entanglement. That's a kind of classical entanglement. It's when two states, in this case the colors of the balls, are correlated in such a way that information about one gives you information about the other.
Right.
What makes quantum mechanics different is that, well, in quantum mechanics, the state does not have to be a definite possibility. So a quantum mechanical state can include things like the probability cloud of an electron around a proton, where you don't know exactly where the electron is. You just know what its probability distribution is. And so entanglement between quantum states doesn't necessarily mean that you know definitively something about one and definitively something about the other. It does, however, mean that information about one gives you information about the other. So there's a correlation between the states. Mm-hmm. So that's more or less what quantum entanglement is. It's not that different from the classical version with the balls, but you have to add in the other aspects of quantum mechanics.
All right. So we've covered a bit of quantum physics. I do have to ask you about the most recently discovered particle, the Higgs boson, the God particle. What is the Higgs boson? What does the discovery of the Higgs boson mean to the world of theoretical physics?
Well, it was a tremendous success, and it was not a surprise to theorists in that area. Yeah. We knew that there had to be something there. Mm-hmm. But the fact that when I say new, it means we had theories that predicted with very high confidence that it had to be there. Yeah. But then we found it, and it has the properties that were expected. It had never been seen before. So it's a validation of the approach that physicists take to the universe. Mm-hmm. And it was an enormous experimental effort. It took a large amount of people's time. Thousands of people were involved in this. A large amount of money, a very large ring around which these particles are accelerated. So it was a huge project, and it succeeded brilliantly. So it's a wonderful discovery. What is the Higgs particle? It's a scalar particle, and it's the only scalar particle that we know of. So that by itself makes it interesting. Every other particle that we've discovered that we think might be fundamental, at least, is a particle that has spin. Electron, for example, is a fermion with spin 1/2. So is a proton. Mm-hmm. The photon, the particle of light, has spin 1. And if there's a graviton, the particle that carries gravity, it would be spin 2. So everything we know has spin, with the exception of the Higgs boson. That's the only possibly fundamental particle that's a scalar. And it turns out scalar particles are hard to understand for a lot of reasons. So the Higgs is a mysterious particle. And it also plays a very important role in the standard model of particle physics. It explains why some particles have mass and some don't. And it explains why the forces that control nuclear decays, there's a force called the weak force, mm-hmm. which is important when radioactive materials radiate.
Yeah.
Okay. It explains why that's a very short range force. It's because the Higgs particle gives mass to the carriers of that force. And when the carriers of a force have mass, it means the force is very short range. It's only effective over a short distance.
Okay.
So it plays a very important role in understanding the makeup of the fundamental forces of nature, why particles have mass. And if it hadn't been there, the whole theory would have been nonsense. It didn't literally have to be the Higgs. There were some other possibilities that didn't make a lot of sense, but at least early on, before we had better data, there were other possibilities besides the Higgs, but there had to be something at the energy that this recent experiment was testing. If not, the theory would have made no sense mathematically.
The discovery of the Higgs did validate the theories that we had, but it also, in a way, highlighted some of, like, we were expecting more, or we were expecting to see some more particles, and as a result, they're trying to now upgrade the Large Hadron Collider.
They're trying to upgrade it, yes. Yeah. So what is surprising from the theoretical point of view, although nothing else was needed, strictly speaking, but what is surprising is that there was just the Higgs and nothing else. So I think if you went back 20 years, almost every particle theorist would have told you there's very likely going to be more than just the Higgs. And that has to do with what I mentioned before, that scalar particles are hard to understand. They don't make a lot of sense on their own. So one set of theories, one set of ideas would have the Higgs particle not be fundamental, but composed of particles with spin.
Yeah.
That's, again, still a possibility, but there's no evidence for it. And a second possibility that would have helped with this conundrum would have been a whole set of other particles, super partners, so supersymmetry. And that would have resolved the thing that's hard to understand about scalar particles.
What is supersymmetry?
Yeah, so supersymmetry is an idea that dates back again some time. But the easiest way to understand it is to say that every particle has a superpartner. Mm-hmm. So there are two types of particles: bosons, named after Bose, an Indian physicist, and fermions, named after Enrico Fermi. Bosons have integer spin, 0, 1, or 2, and fermions have half integer spin, 1/2 or 3/2. And what supersymmetry says is it says every particle has a superpartner, every boson has a fermionic superpartner. And in the case of exact supersymmetry, where that's a symmetry that's perfectly, respected by the world, then those two superpartners have the same mass, exactly the same mass. So one is massless, so is the other. One has a certain mass, the other one has the same mass. And their interactions with other particles are not exactly the same, but in a sense they're the same. They're governed by they're governed by a very strict set of rules that come from supersymmetry. So that would be exact supersymmetry. Now, we knew that the world was not exactly supersymmetric because we don't see superpartners among the particles that we detected prior to the Higgs. But people thought that there might be an approximate supersymmetry. And that would explain the mystery of scalar particles. It would make it easier to understand why the Higgs is relatively light, has the mass that it has. And however, we don't see any of those superpartners. And so now that idea has, I wouldn't say it's gone away, but it's certainly less popular than it used to be. So that side of it wasn't so successful. But that's not why why the Large Hadron Collider was built. It was built to discover the Higgs. Because again, we knew there had to be something there. There was. So in that sense, it's a success.
So we've laid the landscape. We've spoken a bit about quantum physics, spoke about the Higgs boson as well. Let's try to go even deeper.
All right.
Let's try to go even smaller with string theory. What is string theory?
Yeah, so string theory has, again, a long history, which we can go into if you'd like.
Sure.
It originated in attempts actually to explain what we were just discussing, to explain the structure of particles that were being discovered by particle accelerators back then. And what it looked like is you had a series of particles which behaved as though they were connected by a sort of a stretchy elastic string. So as if you had two heavy particles connected by a string, and those particles could rotate around each other, and that would give them some extra angular momentum, some extra spin, and also some extra energy. So two heavy particles connected by a string with some elasticity to it, so they can rotate, they can spin. You can imagine two heavy balls connected by a rope. You could throw it up in the air with some spin, and it'll rotate. And this being quantum mechanics, the amounts of rotation are quantized. So the allowed angular momentum of that system is quantized. It can't be anything. It has certain discrete values. Mm-hmm. And also the mass, the energy associated with those motions, it corresponds to the angular momentum in a particular way.
Okay.
And that fit the pattern that was being observed back then. What we now understand is that it's not literally a fundamental string which is responsible for those patterns. It's rather what's called the strong force, the force that binds protons and quarks and neutrons together into atomic nuclei. And that force does act in many respects like a string. Mm-hmm. And that's why they were seeing those patterns back then. So that's how it started. But when people started to investigate what would be the consequences of a theory like this, where there's a string-like objects, they uncovered a fascinating mathematical structure. And physicists are always intrigued when they come across something like that, something very rich and complex. We have a tendency to think, if this exists, if this structure is there, it's probably used for something in nature. That doesn't always turn out to be the case, but whether it's the case for string theory, we still don't know for sure. But anyway, people got really interested in that and studied it, delved very deep into it. And they discovered that string theories have certain features that really do make them look a bit like the physical world. Probably the most interesting is that they contain a massless spin-2 particle. So I mentioned before that if the force of gravity is mediated by a particle, it has spin-2. Mm-hmm. And it would be a massless spin-2 particle. And string theory always contains a massless spin-2 particle. Now, this was really interesting because string theory is a quantum theory. We understand how to make it a quantum theory. But prior to the existence of string theory and the realization that it contained this so-called graviton, no one knew how to quantize gravity. And to date, string theory is really the only way to quantize gravity that appears to make sense. There's been lots of attempts to do it in other ways. A little bit of progress has been made, but not much. I think it's safe to say that string theory is the only quantum theory of gravity that we have to date. So Does that mean it's correct? No, but if you're interested in how to understand gravity at the quantum level, it's really your only, the only bet that you have, the only theory you have where you can study that. And understanding gravity at the quantum level is a really fascinating thing. So questions about Hawking radiation, for instance, that's when black holes are not actually black but radiate. Questions about the origins of the universe, the Big Bang, multiverse. These sorts of questions mostly, to get into them deeply, necessitate a quantum theory of gravity. And so people have been studying string theory with a lot of excitement since then. And like I said, to date, we don't know for sure that it's the right theory. So one of the strange things about string theory that is probably the most hard to understand is the fact that it doesn't make sense in 3+1 space-time dimensions, 3 space and 1 time. So the versions of string theory that we understand make sense only in 9 space and 1 time dimension. And then you may ask, where are the other 6? And what we've learned is that theories that contain gravity in the form that I mentioned, that have a massless spin tube particle. So those are theories that look like what Einstein predicted gravity should look like back in around 1916 or so. Einstein's theory says that space and time are dynamical. They're not rigid, fixed structures. Mm-hmm. And the geometry of space, which sounds like an odd thing to say, but it's a concept that makes sense, is something which changes with time. There's a set of equations, differential equations, which govern how space evolves over time. So Einstein was able to explain gravity that way by space-time curvature. So in a theory that has extra spatial dimensions, if you want to explain why we only observe 3, what you need to do is say that the other 6 are compactified. That's a little bit familiar to people who played old arcade games like Asteroids. Yeah. Where if something goes off the screen on the right, it pops up again on the left, or it goes off the screen on the top, it pops up on the bottom. Yeah. So if you think about it for a little bit, you realize that 2-dimensional screen is actually the surface of a bagel or a donut. It's a torus. There's 2 cycles. You can go around one way or the other way, just like you can wrap around the bagel the short way or the long way. If you're stuck on the surface of the bagel, it's like being in that game of Asteroids. So that's an example of compactifying directions.
Is the Calabi-Yau manifold also a subset of the compactification?
Yeah. Okay. Yeah. So Calabi-Yaus are manifolds that have certain special mathematical properties that make them very interesting candidates for what these 6 dimensions could look like. But the simple version is just you put what are called periodic boundary conditions, like in the game of Asteroids, on those 6 dimensions. And as long as the distance you have to go before you come back to where you started is sufficiently short, you won't be able to tell, you as a much larger observer, won't be able to tell that dimension is even there. So it's probably a little bit hard to wrap your head around, but yeah, I'm trying to think if there's one way to think about it is that if you are going to come back to where you started when you wrap around this direction and go a certain distance in this direction, then either the quantity you're talking about doesn't depend on that direction at all. Either it's constant, in which case, of course, it can exist in that space, or it does depend on that direction. But if it does depend on it, it has to vary pretty rapidly. It has to change rapidly enough that whatever change it goes through is complete by the time you come back to where you started. So as you make this distance shorter and shorter, you're asking for anything that isn't constant to become extremely rapidly varying. And in quantum mechanics, to have something that varies very rapidly always corresponds to a lot of energy. So if you had really like an electron probability cloud, let's say, around a proton, and you want to say that probability cloud depends on this compact direction, it's different at different points on the compact direction, but it makes sense. So it comes back to its same value it had when you go once around. Then that probability cloud has to be a function which varies really rapidly over a very short distance. It goes through a full cycle of variation. And again, in quantum mechanics, that means a lot of energy. So if you did have a probability cloud like that, it would correspond to an extremely energetic state. And that's why we don't see it when the direction has a very short distance associated to it, because anything that depends on that direction would be extremely energetic, and we wouldn't be able to produce it in a particle accelerator, and we certainly wouldn't see it in our everyday world. So bottom line, at low energies, nothing depends on these extra 6 dimensions. Everything is completely uniform and constant with respect to those directions and depends only on the other 3. And so our experience is as 3-dimensional observers.
How do you even work with a theory with 10 dimensions. I feel like my intellectual ability already low as it is. How do I even try to imagine 10 dimensions? Like, do you think this is always going to be a limitation of the progress we make, that we are not able to think beyond 3 dimensions in space and 1 dimension in time?
I don't think so, because we don't really have to be able to visualize it intuitively. There's already plenty of things in physics that are really non-intuitive. I mean, in fact, almost anything, if you think about it, if you delve deeply enough into it, stops being intuitive and kind of ceases to make common sense after a while.
Quantum physics.
Quantum physics is an example, but the same thing, just pick almost any topic, right? Neuroscience, computers, I mean, almost anything. You dig deeply enough, and things get really weird. So it's more a question of acclimating yourself to these ideas and developing cognitive tools that let you approach them in a productive way. If you want to understand extra dimensions, well, a common way to do it is to start thinking about 2 dimensions and how things would look if you lived in 2 dimensions, and what the 3-dimensional world would look like, and how you would conceive of that if you're a 2-dimensional creature. And there's a famous book by Edwin Abbott called Flatland, which is fun to read. He wrote it back in the 1890s, I think. It's a social parody, but it's like that. There's these 2-dimensional creatures, but they actually live in a 3-dimensional world. And if say something shaped like an apple or a ball impinges on that 2-dimensional world, it starts as nothing, then it's a point, then it grows as a circle, it reaches a maximum size, that's the equator, and then it shrinks again. So after a while, those kind of features, they extend to higher dimensions as well. And so you can develop a set of techniques, tools, mathematical rules that allow you to analyze these theories, even though I can't visualize 9 dimensions. No one can visualize 9 dimensions.
Well, if you can't do it, I definitely can't do it. So obviously 2 of us. Okay. So we covered some of the basics of string theory. Gerard de Hooft, I'm sure I'm butchering the pronunciation, but the Dutch physicist, he believes that we can go even deeper than string theory. And he goes on to say that there is some substructure to the world, which is classical in nature, deterministic in character, which somehow by some mechanism emerges as quantum mechanics. So the wave function, uncertainty, entanglement, all these concepts we spoke about, these are emergent properties of this substructure. Do you think there's merit to this argument? Can we go even deeper than string theory? And if so, what might that look like?
So Gerard de Hooft is an absolutely phenomenal physicist. He's a Nobel laureate, made major contributions to quantum field theory. Brilliant guy. I don't like his ideas about quantum mechanics. I don't think they're correct. Yeah. And I've actually talked to him about it. I've spent quite a bit of time reading some of his papers and discussing them with colleagues. None of us can make sense of them. And he's pretty much on his own in that particular direction. So where he's coming from is understandable. And there's a long kind of intellectual tradition of that in physics, which is people really don't like quantum mechanics. It doesn't make sense to them. It doesn't fit their intuitions for how the world ought to be. Yeah. And so they try as hard as they can to find an alternative, something which will explain all the phenomena that quantum mechanics explains, but not actually be quantum mechanics. And in particular, what people don't like is they don't like the randomness of quantum mechanics. They don't like the notion that a wave function can describe a probability cloud where a particle could be in one place or the other. They want a theory that's more like the one we were used to, where the particle is definitely one place or the other. Maybe you don't know. You might not know where it is, just like Alice might not know what the color of the ball is going to be when she opens the box, but it's got to be one or the other. So that's true in classical probability theory. It's true in classical physics. Mm-hmm. And so there's a long history of people trying to find a formulation of physics like that, where there's a definite answer and it's just your ignorance that accounts for the uncertainty. The problem is that because of things like entanglement and the wave function, the wave interference nature of quantum mechanics that I mentioned before, it turns out you cannot explain the results of experiments with any classical theory, no matter what it is, in which, when I say classical theory, with any theory, in which positions of particles, for instance, or other observables take definite values. Now, obviously, a statement like that is a very, very general statement. How could I say you can't explain it with anything if we don't know what all the possibilities are? So there are some assumptions built into that statement. But really all those assumptions are that there's a definite value for everything, even if you're ignorant of it. And physics is local. So when Alice opens her box, there isn't any influence that instantaneously affects the color of Bob's ball. So once you say physics is local, and you cannot have a classical theory, a theory with definite results for experiments, that is in agreement with the predictions of quantum mechanics. And there are certain specific predictions like that, which have been tested. So, of course, many predictions of quantum mechanics have been tested, but not all of them would, suffice to rule out this other possibility of these classical theories. But there are certain specific experiments that people realized if they turn out the way quantum mechanics predicts, that rules out conclusively any of these alternatives. Those experiments have been done not so long ago, and the results were consistent with quantum mechanics and inconsistent with these so-called local hidden variable theories. Now, a Tufts theory, to the extent that I can tell, is a local hidden variable theory, and it's just ruled out experimentally. So, also, by the way, I don't think this has a whole lot to do with string theory. If this were correct, you could have a string theory. It just means you don't have to think about quantum mechanics, really.
Yeah.
I guess I don't know what the implications would really be. It would probably change a lot of things. But you could certainly, there is such a thing as classical string theory. There's nothing, you don't need quantum mechanics to discuss string theory, really. It's just that what makes it interesting is that it's a quantum version of gravity. So I think, personally, we're looking at everything backwards when we think about quantum mechanics and classical physics that way. I think we ought to say quantum mechanics is right. We could be wrong. Maybe it's not right, but it's the most successful theory we've ever had. The fact that we find it non-intuitive and hard to understand is our own failing, right? Why should the universe be easy to understand? It's actually shocking that it's at all easy to understand and we can make any progress at all.
Yeah.
We have all this evidence that quantum mechanics works. And I think it's a beautiful theory. Yeah, it contains things that we don't like and that look strange to us. But that's why I study physics in the first place, is to learn new things that are interesting, not to just have my sort of old prejudices and biases reconfirmed. I want to be surprised. I want to be challenged. I want to be shocked by things. So I like quantum mechanics for that reason. And I think we ought to be asking not, can we replace quantum mechanics by a classical theory, but rather, can we understand why the world looks classical, given that in fact it's actually quantum mechanical?
I'm going to cite some people who disagree with you.
Please, yes.
Okay, let's start naming names. Richard Feynman, I'm sure this name rings a bell to you. He had called string theory a research dead end. Lee Smolin has said that string theory makes no new testable predictions. Peter Voigt goes as far as saying that string theory is not even wrong because you can't even test it out. Eric Weinstein once described string theory as affirmative action for mathematically gifted people who don't want to understand the real world. Tough crowd.
Okay.
And your colleague at NYU, Pascal Wallish, who was on this show a few months ago, he went as far as saying that string theory is like a religion and physics is at a standstill because of it. It's become cool to hate on string theory for some reason. So first, can you step into the shoes of some of the critics of string theory? And can you present the argument as they were here today? Can you steelman the argument?
Sure. Yeah. First, let me just separate two things. So there's quantum mechanics and there's string theory. What we were talking about just a moment ago, Gerard de Hooft, it's really about quantum mechanics. Yeah. And again, like string theory is a particular theory that is most interesting when you consider quantum mechanics, but there's a classical version. So just to separate those things. Now, why is string theory controversial? I think it's for a good reason. I think these critics have a point. It's not that they're just haters or something. They really do have a point. So what distinguishes science from not science? Really what distinguishes science from not science is falsifiability and to some extent predictivity. So a scientific theory should be able to make statements that you can go and test in a lab, and there's the possibility that those statements will be proven false, or at least the evidence will indicate that they're false. And if that happens enough and you have enough confidence in the experiments, then you will abandon that theory. The theory will be said to be falsified. Mm-hmm. And that's a standard definition of science. It goes back to Karl Popper, and probably before. It's not really the way science is actually done, but it's close enough for I think, for these purposes.
Yeah.
So the real question, if you want to, a lot of these people, like if they say string theory is not even wrong, for example, what they mean is it's not making predictions which we can go out and test and therefore possibly falsify. So, first of all, I think we have to distinguish between classes of theories and individual theories in the following sense. If we get rid of string theory and we just stick to what we are very confident is a reasonably accurate description of particle physics, so that's the standard model of particle physics. The standard model of particle physics is a specific quantum field theory. Mm-hmm. It has a certain very specific set of interactions. It has masses for the particles, values for the coupling constants. There's a set of around, 15, 20 numbers that you input into that theory, and then the output are predictions for particle experiments, for instance. So it's one in a class of theories. Now, many of those numbers are not perfectly well known. So there's still uncertainty around precisely which quantum field theory it is. And when you do an experiment, which is more precise than has been done before, you could use that to refine your knowledge of those numbers. So you can imagine you take the space of all quantum field theories. It's like a big, apple pie. And now you take a slice of that, which are theories that look a lot like the standard model, and then maybe a smaller piece, which are the theories that are consistent with current observational constraints. Still not that small, because again, there are still uncertainties in these parameters. And then every experiment refines it a little more. So you're kind of cutting away theories that aren't right, and you're left with theories that might be right, but you don't know which one. So string theory is a little bit like that. There are different versions of string theory, and within string theory, there are many different solutions which might describe a world if you were living in it. And it's hard to say, it would be hard to come up with an experiment that would falsify every possible version of string theory. But in fact, the same thing is true of quantum field theory. It's impossible to come up with an experiment that falsifies every possible version of quantum field theory, or at least I don't know of one. It's easy to come up with experiments that falsify specific versions of quantum field theory.
Mm-hmm.
So really what you want is experiments to be able to constrain what are the possible theories within some set. That's really what you want.
Yeah.
And in string theory, that is definitely possible to do. For instance, all string theories contain gravity of the form that Einstein predicted. So if it turned out that gravity was not the form that Einstein predicted, string theory is falsified. All string theories are Lorentz invariant relativistic theories. If it turned out that the speed of light is not a limit, relativity is wrong, or at least it's not what we thought it was, you could falsify string theory that way. The problem with these ways of falsifying it is that they were already known. It's like before string theory was invented, people already knew that probably gravity is what Einstein said it was. After all, that was in 1916. And similarly with relativity, that was even earlier. So they weren't new predictions, but they are nonetheless falsifiable predictions. So to say that string theory is not even wrong, or it doesn't make falsifiable predictions, that's not true. To say that it doesn't make predictions that are novel, that we can test experimentally, that has a bit more meat to it.
Gotcha.
And now, why is that true? Why is it so hard? It's basically because what makes string theory interesting is that it's a quantum theory of gravity. You're putting together quantum and gravity. And now it's surprising to many people, but gravity is an incredibly weak force. It's absolutely feeble compared to all the other forces. And one way to explain this is imagine a magnet and a paperclip. So you can pick up the paperclip with the magnet. You can hold it above the paperclip, and the paperclip will move upward and get stuck to the magnet. And it's doing that against the force of gravity. So the paperclip is being pulled down by the force of gravity of the Earth. The Earth is a massive object, extremely heavy. The entire Earth is pulling on the paperclip. And then this tiny little magnet is pulling on the paperclip with a different force, not with gravity, but with electromagnetic forces. Yeah. And yet the electromagnetic forces win. Mm-hmm. So gravity is much, much weaker. Even though you have this huge planet, it's much weaker than electromagnetic forces. Okay, so gravity is a weak force. Quantum mechanics is hard to test. We didn't even know about it until a little more than a century ago, because it affects things on small scales and in subtle ways, mm-hmm. unless you know how to do sophisticated experiments with high precision. Okay, you put these two things together, talking about quantizing the weakest force by far that exists in nature. It's really tough to do experiments on quantum gravity. And this has nothing to do with string theory per se. Any theory of quantum gravity is going to have the same problem, probably. Maybe there'll be a surprise. It'll make some prediction that we didn't think of. But at first glance at it, you would say it's going to be really difficult to distinguish between competing theories of quantum gravity, because it's just really hard to measure any quantum effect in gravity at all. And so that's what it really boils down to. Now, does that mean we shouldn't be thinking about it? I don't know. I think, people believe if someone says it's a religion, that's going way too far. It's certainly not a religion. I can promise you that. There are nobody's worshiping anybody. When I was a graduate student starting my PhD, that was it was one of the peaks of excitement around string theory. So it was when many people my age at the time were going into it because it looked so interesting. But even then, there were plenty of skeptics around. You've got smart people who are putting their careers, or deciding what to do for their careers, right? They could do a lot of different things. And some of them decide to study string theory. Are all those people some sort of, religious fanatics or idiots to do this? Of course not, right? They're making this decision because it looks exciting to them.
Yeah.
It's not inhibiting the progress of physics. That's nonsense. I'm sorry, but that's just nonsense. There's everybody now, especially now, but even back then, everybody now that studies string theory learns all sorts of other techniques in physics. They are actively engaged in studying condensed matter systems, classical theories of gravity. There's all sorts of connections to different fields, like superconductivity, for instance. And scientists, to make a name for themselves, they need to discover something new, something interesting. If it's something testable that gets confirmed, that's the best possible outcome. But you're not going to be able to survive. You won't get a job if all you do is narrowly string theory, mathematical nature of it. That's very, very, very difficult to find a position. You really need to work on something else besides that. You got to work in cosmology. You got to work in astrophysics. So it's just not. It's much less monolithic than I think one might think from listening to these critics. And there isn't really. I have a lot of colleagues that know string theory, teach classes in it. They use it sometimes. Not one of them is just a string theorist. That applies to me as well.
Yeah.
We all do other things too. It's just one of many mathematical tools and ideas that we have at our disposal. And so, yeah, it might be the right theory. It might not. It would be more exciting if it isn't, because that means there's something new that we haven't discovered yet. Mm-hmm. And everybody agrees with that. If you could prove that string theory doesn't make sense, maybe it's illogical, like it's logically inconsistent, that would be fantastic. You'd become very well known if you could show that. Everybody would be really happy about it, because now they could go and learn whatever is replacing it. They could study that inconsistency and try to figure out how to fix it. It would be a really exciting thing. So yeah, it's very different from religion, where people just aren't allowed to question the faith, really. It's exactly the opposite. We're all actively trying to knock it down and destroy it and shave away more pieces of that apple pie. Yeah. Because that's how you make your name for yourself, and that's how you discover something that wasn't known before.
Okay.
Oh, but you wanted me to put myself in the place of these critics and make the argument for them, which I don't know if I did that.
Well, you presented the argument and you provided a response to it. I think we covered both, because the next question is going to be what's going to be a response to it. So you anticipated the question ahead, and you brought it together. Okay. We've made the case for string theory. We've also spoken about the implications of it. You mentioned that's not the only thing you do. So let's talk about the second big theory for this conversation, which is the multiverse, a term that you dislike because it implies that there's something beyond the universe. You prefer using the term bubbles or regions. But for the first question, just to introduce the topic, I'm going to use a colloquial term. What is the multiverse?
Yeah, so and it's a great question. People use that term in different ways, actually. So we should also delve into that just a little bit. So I think the simplest kind of multiverse is just to say there's an observable universe. Mm-hmm. And what does that mean? It means that we look out with the most powerful telescopes we have, the most powerful instruments we have, and there's only a certain limited distance that we can see out to. The reason for that is fundamentally because the universe had a big bang, and it has therefore a finite age, 14 billion years. Light travels at a certain speed. So 14 billion years times the speed of light gives you the distance that you can see. Now, that's not quite right, because the universe was expanding. You have to worry about general relativity and the geometry of space-time and so on, but it gives you a sense. There's a limit to how far you can see. And so beyond that distance, we don't actually know what's out there. And anything we say about it is just inherently speculative, and it relies on assumptions about theories. So whatever's beyond the edge of the observable universe, maybe it's nothing, maybe it's more of the same, maybe it's something totally different. That is a kind of multiverse, right? We live in a bubble, if you want, a region that's bounded by a horizon beyond which we can't see. And whatever's beyond is unknown. Well, that's kind of the simplest, least controversial version of the idea of a multiverse. It's a bit like saying you live on an island in the middle of a huge ocean. You climb to the highest point, and there's a limit to how far you can see. You can see 30 miles, 20 miles, whatever, depending on how high the highest point is. You don't know what's beyond. There might be other islands, might have other people on them. There might be just more ocean. There might be the edge of the earth with all the water falling off. Who knows? So that's the simplest version of it. And when you ask, the current theories that we have, the theories that seem to fit data the best and the most coherent theoretically and so on, what do they predict? They seem to predict something really interesting. If you were to go far enough beyond the observable universe, that you would discover this very rich structure of other bubbles, other regions, some of which would look completely different from what's around us, others of which would be very similar. So that's the idea of this kind of bubbleverse, or a huge universe that's
different in what way? Sorry.
Well, if string theory is correct, so we mentioned earlier that string theory has these 6 extra dimensions. Yeah. And those dimensions have to be curled up. They have to be compactified. in the region that we're in. Otherwise, we would have noticed them.
Yeah.
But we also said gravity makes geometry dynamical, or it makes the geometry of space-time dynamical. It makes it change with time, and it can change with position. So one thing that can happen is as you move around, you may discover that those extra dimensions are no longer curled up so tightly or hardly at all. So there might be a different number of dimensions, or even some of the 3 dimensions that we see here could get curled up, and then it'd be fewer dimensions. So that's really different. And that's pretty hard to visualize.
Yeah.
But imagine a cylinder, like a pipe, and you live just on the surface of that pipe. So you can walk left or right along it, or you can circle around it. But if circling around it is a sufficiently small distance, then for reasons we said before, you wouldn't even know that direction is there. You would live in this one-dimensional world.
Right. Yeah.
Now, suppose you go a long distance down this pipe and it gets bigger and bigger and bigger. So now all of a sudden it has a very large radius. And now anyone will notice that you can walk around it. So that's an example of how you can go from effectively a one-dimensional world to a two-dimensional one. And that is the sort of thing that could happen in these other regions. Now, of course, if you actually went down there, you would not be able to exist anymore, because not just the human biology, but the fundamental particles you're made of don't even really exist in the same way in these other regions. They don't make sense in different numbers of dimensions. They're not truly fundamental if string theory is right. And so not only could you not live, but it's not a question of needing a spacesuit or something. The fundamental stuff that you're made of wouldn't even exist. So there's no way to actually go there and experience that, unfortunately. It would be kind of fun to be able to take a walk in some extra dimensions, but that's not going to happen. But one thing I've worked on in the past is, are there signals? Could we do observations that would lead us to believe that this really is correct, that there really are these regions? So anyway, so that's a version of the multiverse. The last version has to do with quantum mechanics. And this is more the one that's been popular recently in movies and so on. And that's the idea that there are multiple possibilities, which in some sense are real. And one way of thinking about quantum mechanics is when you make a measurement, you get a certain result. Mm-hmm. The result seems to be random, and it's randomly selected from a set of possibilities. So you could imagine, for example, flipping a coin. Classically, just flip a regular coin, you get heads or tails. And of course, you get one or the other, and then you forget about the other possibility because it's not relevant to you. But if you wanted to, you could say, well, imagine the world is sort of split into two, and there's a version of me that sees heads and a version of me that sees tails. And they're never going to interact with each other. They don't really exist in the same space, but you could keep them both. And then maybe they flip the coin again, and now there's 4 versions of you, and so on. And you follow a certain path through this tree. The rest of the tree is there, if you really want to think about it, as a set of possibilities. So one interpretation of quantum mechanics is that those possibilities could interact with the one you're in. And they don't generally, or at least the effect they have is so small that we don't notice it. But for microscopic experiments, for example, if you flip a coin for a particle, you could send light through a mirror, which is half silvered. So the light can either reflect or transmit. And it has about a 50% chance of doing either one. We send a bright beam of light through, it'll split into these 2 paths. Send a single photon through, it'll follow both paths in some sense. So both of those possibilities will be represented in the particle's wave function, and they will then interfere later.
This is the many worlds theory.
This is the many worlds interpretation of quantum mechanics. Yeah.
So just so I get it right, at any given point in time, there's these multiple forks in the world that are happening at the same time, and those worlds exist. It's a probability. What's happening?
So the term exist is an English word, which refers to a set of concepts that we have all developed from our ordinary experience. I just 2 days ago gave a lecture in my quantum mechanics class about this precise point. Mm-hmm. And I gave an example of an experiment where you have what I was just mentioning, a beam splitter, that it's a device, a half silvered mirror that splits a beam of light into two parts. It's like sometimes at a circus, there's one of these mirrors where 2 people can look and they'll see the combination of their faces. Yeah. That uses these things. Yeah. And the results of that experiment, when you turn down the light source so that only single particles are going through, single photons at a time, cannot be explained by the particle flipping a coin and following one path or the other. They also can't be explained by the particle splitting into 2 half particles and following them both. And they also can't be explained by the particle following neither of these 2 paths, which just seems to rule out every possibility. And in fact, the truth is that the particle evolves into what's called a superposition. It's an English jargon term that physicists have developed to describe this new way of being. Now, Does that mean that the particle exists on both paths in two places at the same time? Depends on what you mean by the word exist. And, I don't want to argue semantics, but there's a mathematical structure which just isn't, it's not or, it's not and, it's not neither. It's not both, right? It's something else. It's a superposition. So that's the sense in which these multiple versions are there. They're in the wave function that describes everything, including you, the experimenter that did the experiment, is a superposition of quantum states. And in each part of that superposition, you may have gotten a definite result, but it's a different result in each of these branches. That's this many worlds interpretation. And, a lot of these movies about the multiverse are playing off of that idea, of course. In reality, you can't go back and forth between these. They don't affect each other for macroscopic superpositions in any way that we've ever detected. The only place where you really see this as an important physical effect that you can test is for tiny systems consisting of just a few particles, not an enormous classical object like a human being. And so we don't really know whether this is the right theory, but it's the right theory for small experiments. It's pretty natural to extrapolate it to the large. So that's the last version of the multiverse. And like many other things in physics, these ideas are actually connected to each other. Yeah. Because in quantum mechanics, anything that isn't forbidden will happen. It's sometimes called the totalitarian principle for some reason. And so there's nothing that forbids transitions between different compactifications, different geometries of space, for instance. So even if the universe started off in a state where everything had, let's say just 3 large dimensions and 6 compact dimensions, occasionally a quantum fluctuation, a quantum event would lead to part of the universe making a transition to a different state, where now maybe instead of having 3 large dimensions, it has 5 or some other number. And those regions are around, but really what happens quantum mechanically is that the wave function of the whole universe evolves into a superposition, where on some of the branches, everything is still as it was. And in other branches, there's been this event where a bubble appeared. Mm-hmm. So the multiverse that has all this rich structure beyond the horizon truly is a branch, or the whole thing really is a wave function with many branches. So that's the sense in which these 2 notions of the multiverse are connected to each other. It's an interesting story.
It's an interesting story. I don't want to get lost in the semantics, but I guess my understanding is there's multiple quantum states in which we're having this conversation, and we just happen to be on one of those branches of it, right? Which is completely arbitrary.
Yeah, that's a good way to think about it. Yeah, right.
I don't know if that's a good way to think. My brain is broken at this stage.
Well, it's tough. I mean, it's one of these things again where our ordinary intuition, right? We talked about extra dimensions. It's really hard to conceive of. Yeah. This is even harder to conceive of. Yeah. And this is again one reason why people hate quantum mechanics. They don't want to have to think about this crazy story. It sounds completely nuts. And so it's like the problem child of physics. It's been rejected by physicists since inception, pretty much. No one likes it. Well, not no one, that's too strong. Many people don't like it. But again, I think as long as it's consistent with what we observe, we shouldn't let our own biases about what we expected to find get in the way. And not only is it consistent with what we observe, it's incredibly successful. It describes everything that we apply it to. It never seems to fail. It's just that in some cases, it's hard to see the effects of it, like quantum gravity or a superposition of macroscopic objects. Those things the effects are tiny. The difference between quantum mechanics and classical physics is tiny, so it's really hard to see. But everything where you expect the difference to be large, quantum mechanics works. So why not just assume it describes everything and then see what the implications of that are? I think that's a more interesting approach than kind of swimming against the tide and trying to find a different theory that doesn't have these uncomfortable implications. Yeah. Anyway, so that's yeah. But again, in the first version of the multiverse, where it's just regions beyond our horizon, possibly different from our own, that doesn't even really require quantum mechanics. The initial state might have just been sort of random, and so maybe the region we're in it's very large, so that's all we see. But there could be a lot of stuff beyond it.
Okay. Lots to think about. A few things you mentioned in your description of the multiverses. Let's pick one. you spoke about the universe is expanding. And so if you want to actually measure the event horizon of the universe, you multiply the speed of light. By the time the universe has existed, you will get the event horizon for it. But the universe is also expanding in the middle, in pockets in between. So let's go there. You brought it up. You opened up this can of worms. So now we're going to go there.
Sure.
Around 20 years ago, you wrote a paper with the legendary Leonard Susskind and Lisa Dyson titled Disturbing Implications of a Cosmological Constant. In the abstract, you said that we argue that these assumptions inevitably lead to very deep paradoxes, which seem to require major revisions of our usual assumptions. What is the cosmological constant? What problem does it pose in theoretical physics? What disturbing implications, deep paradoxes does it give rise to?
Yeah, so that's a very interesting can of worms. I'm glad you opened it. So what's the cosmological constant? It goes back to Einstein. When Einstein was writing down the equations of general relativity back in the 19-teens, the prevailing view among astronomers was that the universe was static. So they believed that the universe was more or less the same as time passed. It wasn't expanding, wasn't contracting. There were some deep paradoxes associated with that, but there's always deep paradoxes associated with any theory of physics, and that was just what people believed at the time. Mm-hmm. So when Einstein wrote down his theory, it was essentially unique based on the principles that he was applying to it. There's very little wiggle room for what that theory could be. And he discovered pretty quickly that it did not allow the universe to be static. So I mentioned that the geometry is something that evolves in time in his theory, and a static geometry where you had a bunch of stars and galaxies that just remained at fixed positions simply wasn't a solution to the theory. And the reason is not hard to understand. Even Newtonian gravity, the theory of gravity that came before, wouldn't allow that because gravity is attractive. So the galaxy sticks together because the stuff in it is pulling on the other stuff in it. It's more or less, it's not so different from the solar system where planets orbit around the sun. In the galaxy, stars like our sun orbit around the galactic center just because they're affected by the gravity of all the other stars in the galaxy. Yeah. It's like a big pancake where it's spiraling around, everything's orbiting. That's fine. Mm-hmm. Now you put some other galaxies in though, and those galaxies should be attracting each other. And so why would they remain static? They're not going to remain static. They're going to fall towards each other. In Einstein's theory, still true. And it's a better defined theory than Newton's was, especially when you try to apply it to the whole universe. And it just unequivocally wouldn't allow that. Unless Einstein added one extra term, which was literally the only thing he could add that would have any effect, the so-called cosmological constant. Yeah. And if you added that term and it had just the right strength and just the right sign, then there was a solution that looked static. As it turns out, it's not really static. It's only static if the universe is perfectly homogeneous, which it isn't. It's got galaxies in certain positions. And even then, it's unstable. The slightest perturbation will make it either expand or contract. Einstein apparently didn't realize that. So it actually doesn't work to explain a static universe. But in any case, astronomers shortly afterwards discovered that it looked like the universe was expanding. And then Einstein was rather upset that he had added this term, just trying to explain a static universe when in fact it wasn't, because if he'd had the kind of courage of his convictions and said, my theory predicts a universe that's not static, it's expanding or contracting, and then they discovered it, would have been better. Not that he needed it, but so that was the origin of it. And so then for how long? 70 years, people forgot about it, more or less. Not totally forgot about it, but there was no evidence that cosmological constant was there, so it wasn't considered particularly important. It was just a curiosity. And then the very first physics colloquium that I ever went to when I started my PhD was Saul Perlmutter, who was leading one of two major projects to measure supernova in the universe. Supernova are interesting because supernova of a certain type, we believe, always explode with the same intrinsic brightness. So they're like, if you remember what a 60-watt incandescent light bulb is, it's been a while since anyone used those, but they all have the same brightness as long as they're working correctly. So if you had a bunch of them distributed in the night, you could tell how far away they are by how bright they appear. Yeah. Further away they are, the dimmer they look, you could then infer the distance. Supernova of type 1a are like that. We know how bright they are intrinsically, so by how bright they appear, we know how far away they are. And we can tell how fast they're moving away from us because there's a Doppler shift to light. Like when a police siren goes by you, the pitch shifts down. Mm-hmm. If a light source is moving away, it's Doppler shifted. Yeah. So we can tell how far away they are and how fast they're moving. And then with a lot of them, we can reconstruct a map of distance versus recession velocity, speed moving away from us. And that is what we mean by the expansion of the universe. We mean that things further away are moving away from us faster. And when they analyzed all this data, they discovered that the expansion of the universe was not slowing down, which is what Einstein's theory without the cosmological constant would predict. If you take all those galaxies and you make them move apart from each other, the gravity is still attractive. So the speed with which they move apart will decrease over time.
Yeah.
It may never come to rest. Throw a rock up hard enough, it will never come back to Earth. It will escape into orbit or out of the solar system even.
Oh.
So, they may never come to rest and recollapse, but the speed with which they're expanding should be slowing down. But it wasn't. It was accelerating. It was going faster and faster with time. So there was some kind of repulsive gravity, something that was compensating for the attraction between these galaxies. That's the cosmological constant. So it came back 70 years later, and it was a shock. It was a huge shock. People didn't like it at all. And it's still it's an enormous mystery. Why is it there? But why is it so tiny? It had such a small value that we didn't even know about it until the 1990s, late 1990s, when we could do precise enough cosmological experiments. So that's the cosmological constant.
Why is it expanding? What is dark energy?
Why is the universe expanding at all?
Yeah.
Yeah. So for that we don't need the cosmological constant. Cosmological constant explains why it's accelerating, but why it's expanding in the first place, that's another question. There seems to have been a big bang, massive explosion of a sort about 14 billion years ago, which flung everything outward at very high speed. Why that happened, we can go into it. There's some interesting ideas about it, but it's, for the moment anyway, just an observational fact that it's expanding today. And if you extrapolate back in time, you see that it was at a point about 14 billion years ago. Why is it accelerating? Why does the cosmological constant make the expansion accelerate? There's not a very good intuitive answer to that question. I've been asked it many times. It's, it's related to the fact that the cosmological constant is like a vacuum energy. It's an energy that completely empty space is endowed with. And gravity.
This is dark energy?
This is dark energy, cosmological constant. Those are more or less the same thing.
Yeah.
When we talk about dark energy, what we mean is there's some form of energy that's causing the expansion to accelerate.
Mm-hmm.
We don't know that it's literally a cosmological constant. It could be a form of energy which is close to a cosmological constant, but not exactly like it. So dark energy is a more general term, but it's some form of energy that we can't directly see. We can just infer its existence from the accelerated expansion. So any form of dark energy is at least very close to a vacuum energy. It's an energy associated with just empty space. And so why does that make the expansion accelerate? Well, gravity acts on all forms of energy. So if empty space has an energy, then the equations of Einstein predict that space itself will either expand or contract because there's energy associated with that volume. So it's not going to just sit there. There's a force. There's an effect that causes the expansion rate to accelerate or decelerate. And the sign of that effect, whether it accelerates or decelerates, depends on the sign of the energy. But the sign we need to explain what we see is the one that causes the expansion to accelerate. So that's not a very satisfactory answer, I'm afraid, but what it boils down to is energy of vacuum that's acted on by gravity, and the effect is to change the expansion. And since the energy can have either sign, it's maybe not surprising that it could cause the expansion to either accelerate or decelerate. If you choose the right sign, it accelerates.
You may say it's not a satisfactory answer. I'll take what I can get at this stage. I promise we're going to tie it in together. I think you've already covered a bit of it, but I believe string theory predicts these vacuum energy of different densities, right? So I guess string theory is one possible avenue or one channel that you can take that tries to explain dark energy, which is such a mystery in the universe.
So string theory predicting vacuum energy, that's an interesting topic. What string theory does, as we've mentioned, is it has these extra dimensions, and there are many, many, many different ways to curl them up in such a way that we only see 3 large dimensions. So those different ways of compactifying the extra dimensions give you rather different physics in the 3 large dimensions. And one of the things that changes is the vacuum energy. You can think of that as being related to the fact that when you curl up those extra dimensions, there's some energy associated with doing that. You could imagine why that's so. If you think of the extra dimensions as being like a cylinder made out of metal, something like a soda can, you squeeze the soda can and put a dent in it, you've put some energy into it, and you could maybe release that dent, make a sound, because it would release some energy as it springs back to its former shape. So when you curl up these dimensions in different ways, there's energy associated with that. And since that energy is spread everywhere in the three large dimensions uniformly, because what we said before was, you have these extra dimensions and then you have the three large dimensions, and they're sort of perpendicular to each other. So you have an energy which is everywhere in the three large dimensions. So that's a vacuum energy. Mm-hmm. And so different compactifications of string theory give you different vacuum energy. And one of the ideas is that there are so many different ways to compactify those dimensions. They all give a different vacuum energy. You'll have many, many, many different possible values of the vacuum energy. And some of those are probably consistent with the value we observe. There's a probably in there because we don't actually know for certain that that's the case. We can't say, here are the set of compactifications. Vacuum energy is consistent with what we see. And the reason we can't do that is that, well, the math is just too hard. We don't have the right techniques yet. So, but this is one of the ways in which the multiverse comes in. If you have all these different ways of compactifying, each one has a different vacuum energy. Some of them have different numbers of large dimensions. They have different, actually, properties of particles, interactions, masses of particles, numbers of particles. All that stuff can vary. So cosmologically, in a big universe, you would have this extremely rich multiverse where different regions of the universe have very, very different properties, different vacuum energies, but also maybe different numbers of dimensions and different spectra of particles. So that's one way that string theory can help explain why we have some kind of vacuum energy. Now, why do we have the value that we have? And there is something unusual about it, which is that it's extremely small. Mm-hmm. So we didn't notice it until the 1990s. Why not? Because it's a very, very weak effect. It's something that you can only see when you look at very large scales in the universe. You have to look at galaxies that are very distant from the Milky Way, carefully measure how rapidly they're receding from us, do a complicated data analysis, and in the end, you can infer that there's this vacuum energy. It's a very weak effect. So it's a tiny amount of vacuum energy, really, really small. Corresponds to about the energy in 1 proton per cubic meter of empty space. If you think about it, there's 10 to the 23 protons in a gram, 6 times 10 to the 23 protons in a gram. So in a cubic meter, you have many, many grams of just about any substance, whether it's air, water, human being, table, whatever. A huge number of protons per cubic meter in a typical substance. The dark energy corresponds to an energy of about 1 proton per cubic meter equivalent, right? E equals mc squared. So mass and energy are connected to each other. So tiny amount of energy. Why it's so tiny? Well, if it were much larger, then the universe would be expanding very rapidly, and the expansion would be accelerating very rapidly. And that wouldn't have allowed galaxies to form. Galaxies formed from a state where matter was pretty much homogeneous. You had essentially hydrogen gas, more or less spread uniformly throughout the universe, with just very small inhomogeneities. Some regions a little denser than others. Mm-hmm. Those denser regions had slightly stronger gravity, and it's like the rich get richer. That pulls in more mass, get denser and denser and denser. Eventually, that causes the gas to heat up. And eventually, when it gets dense enough, it will form stars. Stars will start to burn. That's where stars came from. If you had more vacuum energy than we actually have, that would never have happened, because there never would have been a chance for anything to gravitationally collapse like that, or for stars to ignite. The universe would have kept expanding and accelerating in such a way that after a while, every molecule of hydrogen or proton would be just by itself, would have nothing else around it. It would be a completely empty and boring universe. That's with a positive sign of dark energy that makes the acceleration increase with time. If you had a negative dark energy, it would make what you could call deceleration. So the expansion of the universe would slow down more rapidly than it would if it just had matter in it. If you had a large amount of negative vacuum energy, it would make the universe turn around and recollapse and go to what's called a big crunch in a very short time. Again, there'd be no chance for any structures to form. So one theory is that if it's possible to have many different values of vacuum energy, and if different regions of the universe have different values of it, it's only those regions that have vacuum energy around what we observe that contain anything of any interest. So it's only in those regions that you have stars, galaxies, planets, observers, us, to ask these questions. Mm-hmm. So asking why the vacuum energy is so small, it's like asking, why do we live on the surface of a rocky planet, right? The vast majority of the volume of the universe that we can see is empty space. And then if you just ask about interesting objects, well, the vast majority of the volume would be inside a star. Or even you just ask about planets, most of the volume is inside the planet where it's all molten and hot. So why don't we live inside the Earth or in the sun or in empty space? Well, we probably live on the surface of the Earth because that's the only place where life can evolve. And so similarly, if you have a multiverse like this, why do we live in a region with small vacuum energy? That might be the only place life can evolve. So this is called the Anthropic Principle. It's another very controversial approach. People don't like it.
Humans are the center of it.
Yeah, they don't like it because it puts humans into science, which sounds like something you shouldn't do.
Right.
But to me, and the other reason they don't like it is that it's a bit like giving up. You're not trying to explain this in a more quantitative or fundamental way. You're just saying it had to be that way or we wouldn't be here. That's not very interesting as an answer. I agree with those criticisms, but at the same time, I think this is obviously the right answer to certain questions, like why are we living on the surface of a rocky planet? It's people don't even ask that question because it seems dumb. It's obvious what the answer is. I think that's what most people would say if you ask them that question. They would say, I never thought about it, but if you really make me think about it, of course we live on the surface of a planet because everything else is empty or extremely hot or
sure. It's a finely tuned universe.
Yeah, and especially where we live is a very, very specific place, extremely specific. We're within a few meters of the surface of a rocky planet. You divide the volume of regions like that by the total volume of the universe, it's a ridiculously small fraction. Yeah. So we live in an incredibly fine-tuned place. And I think the only possible answer is, well, that's the only place where life is. So I don't see this as all that different. Hopefully there's a better answer. Maybe there's a calculation you can do that uniquely predicts the vacuum energy. That would be much better. I doubt it though. I think this is probably the right answer. I think it's the most compelling of all the solutions that's ever been proposed for it. And there've been many.
You brought up the Big Bang. Where does the Big Bang sit in the multiverse theory?
Right. So the thing we know observationally, the universe is expanding. Think of it as a movie, run that movie backwards, it's contracting. And because gravity is attractive, and in fact, dark energy is only important now, in the past it was irrelevant because it's so small. So as you run this movie back, the universe is contracting and it was contracting faster and faster as you go back because gravity is attractive, things are getting denser. And that means you hit a singularity, a point of, looks like it has infinite density and infinite temperature, roughly 14 billion years ago. So that's what's called the Big Bang. It's an extremely hot, extremely dense phase, which running forward in time again was like an explosion that flung everything outward. Now, we don't know what came before that, if anything. We don't have any direct measurements of it because the universe was opaque back then. It was like a ball of fire, like the inside of the sun, only hotter. So you can't see through that. The sun is opaque. Beam a laser pointer at it, doesn't come out the other side. So you try to look back far enough in time and you don't see that. You run into a wall. So we don't know what came before. But in these theories of the multiverse, where there are these transitions that I mentioned, quantum transitions where regions can appear, in those theories, regions of the universe can pop into existence through a quantum fluctuation, which look very much like the regions we live in, like the region we live in. They produce eventually large universes that are expanding at a certain rate. And that mechanism of producing those regions is not in itself singular. It doesn't involve infinite temperatures or infinite densities. And it's actually possible to understand within these theories using standard techniques that we use for other theories in physics. It's a kind of a first order phase transition. It's not fundamentally that different from a bubble of carbon dioxide appearing in a glass of champagne. It's a similar sort of transition. So it might be that the Big Bang was a transition like that. And if so, it's actually not the beginning of time. There is something before the Big Bang, which was whatever parent state our region of the universe originated from. And it's mathematically, understandable and it's not a singularity that can't be resolved. So this is one possible resolution of the Big Bang singularity. It doesn't actually totally answer the question because that region that our region appeared inside of also had to come from somewhere. And because of this fact about Einstein's theory that I mentioned before, that it insists that the universe is either expanding or contracting, you still have some kind of beginning if you go far enough back. So there's still some initial singularity that we wouldn't be able to understand this way. So it's not a full answer to the question, but the thing that we call the Big Bang, the 14 billion year ago event that produced the region we're in, that one can be resolved this way.
Oh boy. I have a philosophical question for you. I have to ask you.
Please.
It's in my nature.
Yes.
Bernard Carr is famous for saying, if you don't want God, then you better have the multiverse.
Okay.
I'm going to put the multiverse theory on one side. I'm also going to add Roger Penrose's conformal cyclic cosmological theory on the same side.
Yes.
Both implying that there's a cycle to the universe. There's an infinite loop of sorts, that the Big Bang wasn't the starting point. It was just a fluctuation, like you mentioned, within that infinite loop. And on the other side, I'm going to put the Big Bang was a point of singularity. The cosmological arrow of time starts at that point, and there's nothing before it. This also leaves the door open for a creator.
Mm-hmm.
So you have an infinite loop on one side, and you have nothingness before the Big Bang, or maybe even a creator on the other side. Which theory do you fear more?
Which one do I fear more?
Yeah.
Well, first of all, I don't see why the creator has to be only on one side. Maybe the creator created an infinite loop. After all, if there's a creator.
So then this would be a subset of this. Like there is an initial singularity. The creator created the infinite loop, and then that's it.
Yeah, I mean, if there's an all-powerful being, it can do whatever it wants. Maybe it can create things that existed for all time because it exists outside of time itself. Who knows, right? I mean, so I don't really, people didn't like the Big Bang originally because they thought that way. They thought, well, this means that there had to have been a moment of creation, and that sounded religious. So a lot of scientists didn't like it for that reason. Right. The term Big Bang was coined to make fun of the idea. Yeah. So yeah, you're right that that's the way some people think. I never really saw it that way. I think, well, first of all, I think if all the creator did was cause the Big Bang to happen, that's a pretty mild form of religion. I mean, it's really taking it outside the realm of anything that can affect us in everyday life. I mean, if the creator just sort of started the thing going, okay, fine. It doesn't really, it's not a very specific belief. But again, I don't see why the creator couldn't have created a static universe or an infinite cyclic universe or whatever. So I don't really think that plays much of a role, at least not in my thinking. So I don't fear either of these. I think infinite cyclic universes do trouble me, for physics reasons. Okay. Namely, there's no such thing as perpetual motion. That's one of the laws of physics that we've learned the hard way over centuries. Yeah. Whenever someone patents a perpetual motion machine, don't buy stock in their company because it's not going to work. Yeah. There are laws of thermodynamics. Those are called laws because they really seem to apply universally. So a cyclic universe that goes on forever is a perpetual motion machine. Now, obviously, the things that we've learned from steam engines and heat pumps and so on, those laws of physics might not apply to the whole universe. So maybe you can have it. But I haven't really seen a proposal which actually addresses that problem, including Penrose's. Penrose's has a lot of missing pieces in it. But complicated rules of physics or complicated things like the universe that contain a lot of stuff, which can produce entropy. Stars burning produces entropy. Gravitational collapse produces entropy. All these things obey the laws of thermodynamics. How is that going to reassemble itself and go through a cycle that would entail entropy decreasing? It's not plausible, I don't think. So the cyclic bothers me more than the Big Bang, because at least for the Big Bang, as you said, you could start the arrow of time from that moment. For whatever reason, you have low entropy then. It's not really an explanation, but at least it doesn't pose an extra problem like the way the cyclic cosmologies do. So I guess I fear the cyclic cosmologies more in that sense.
Yeah. And interestingly, you put the creator on both sides. So what probability would you assign to a creator? What would be your Bayesian prior? Because earlier we spoke about supersymmetry as well. We spoke about these particles and how some of them have this antithetical particle to it. There's a lot of inherent beauty in particle physics, which brings rise to the design argument and also the possibility of the creator. So what probability would you assign to there being a creator?
Epsilon, where epsilon is less than any positive real number. I mean, I like to think about it like this. Imagine two universes, one where there's a creator and one where there isn't. Okay, if you can imagine that. One where there's a God and one where there isn't. And in both of them, human beings evolve and look up at the sky and wonder where they came from. I'm pretty sure that in both of those worlds, human beings would worship some sort of creator, because I think that psychologically that's very comforting, and it's kind of logical as well in the sense that we're born, we have all-powerful beings, namely our parents, who know everything and provide everything for us and love us and are kind to us. Then we grow up and we realize they're actually fallible and getting old, and it's very natural to imagine that there's another level beyond that, which is not so different, that there's some sort of parent figure living in the sky that created us. I think it's a very, to me, natural belief for people to come up with, irrespective of whether it's true. So the fact that there are religions in the world, to me, is not evidence at all, one way or the other, that there's a creator. So the possible existence of a creator is a hypothesis for which we don't really have evidence for or against. There are many other hypotheses that we also don't have evidence for or against. So looking at it in that sort of rather cold way, I don't see any. Yeah, why would I believe that more than any other choice? Right? So people talk about the flying spaghetti monster or something. You come up with some crazy thing. That might be true. Yeah. We have no evidence for or against it because it's off somewhere where we can't see it. Okay. With that said, I have no problem with religion at all. I think it's perfectly reasonable. It's a fine thing. There's a lot of great traditions associated with it, but I personally don't give much credence to it.
Okay. So it's better to act as if there's a creator, as if God exists. Let's close the loop on the Big Bang, on the universe itself. So we spoke about how it started, explored some theories about what's happening now, whether it's part of a multiverse, whether it was a singularity, just the Big Bang. What happens next? If we travel down the cosmological arrow of time, what's next for us? Is there a big crunch, a big chill, a heat death of the universe, or something else?
Oh, again, we don't know the answer to that. We have to extrapolate, and that means we have to make some assumptions about theory. Yep. The simplest extrapolation from what we're observing is a heat death. It's that the universe will continue to expand, and actually the rate of expansion will continue to accelerate. So dark energy would be a cosmological constant. That's the most kind of parsimonious explanation we have for the current data. And if that's correct, we will eventually reach a state where all stars will have run out of fuel and burned out. The Milky Way galaxy will be by itself, or it will have maybe a few other galaxies that are bound to it, but a small group of galaxies will be by themselves. Everything else will have gone beyond the horizon. That state will persist for an unimaginably long time. So everything will be cold and will be quite boring, but at least there's these sort of dead stars and ice planets and so on. Yeah. If you wait a really, really ridiculously long time, even that will cease to exist because there's an incredibly rare quantum tunneling event where an object which is gravitationally bound to another object can tunnel to a point far enough away where it's no longer bound and gets pulled away by this accelerated expansion. So the ultimate future of this, like on absurdly long timescales, is every indivisible particle is by itself in a huge empty universe. And then if you wait an even more ridiculously long time, as it turns out, the theory of the cosmological constant seems to predict that there's a non-zero temperature. It's just like black holes are not actually black. They Hawking radiate. They have a little bit of temperature. Accelerating universes have event horizons, which are much like black holes, except that they're inside out. They surround us. Those horizons are never totally cold. So there's a tiny amount of temperature and energy associated with those horizons. And the paper you mentioned before, this disturbing implications of the cosmological constant, the point was in a situation like that, where you have a tiny amount of energy and energy is accessible always, eventually any state which ever existed will recur. It will come to exist again. Maybe not quite exactly the same state, but a state that's arbitrarily close to the one you're interested in. These are called Poincare recurrences. These really are examples where the laws of thermodynamics break down, but on absurdly long time scales and in an understandable way, unlike the cyclic universes. So instead of getting a cyclic universe, you get a quasi-periodic one where on these super long time scales, if you specify a state, the one we're in now, you'll be able to find infinitely many instances of it, ridiculously far in the future and actually in the past, where something very close to that state existed.
So this could be an imprint of a previous state.
Yeah, but the timescales are so long. So the timescale is like the double exponential of an enormous number. It's hard to even explain how big this number is.
Infinity, what does that matter?
Well, right. So exactly. So in that paper, we explored the consequences of this and we found them rather disturbing. And interestingly, since you raised a creator, the idea of a creator, that paper has been quoted as a proof of the existence of God. And I personally think it's a pretty good one. If you're going to try to argue for the existence of God, there's some numbers in that paper that you could say this is the probability. And the argument doesn't actually quite hold up, but it's a pretty good try. So it's in some books by creationist scientists and so on.
Yeah, I have one of the quotes actually.
Oh, you do? Okay.
Which said, let me try to find it. One of the articles said that the incomprehensibility of the situation even drives Susskind's team to ponder whether an unknown agent intervened in the evolution of the universe for reasons of its own. Yeah, I think there's strong evidence for a creator. But yeah, so just to close the point on what's next, looks like there's a likely possibility there's going to be a heat death of the universe. So exciting times to look forward to. Can't get there soon enough.
In the next 100 billion or
the next
1 trillion years. Yeah.
I'll be there.
Yeah.
And we can look back.
You'll still be making podcasts.
Yeah, who knows?
Yeah.
And we can look back and be like, yeah, of course, Prater. Of course, that's going to happen. Fantastic. Before we move into final questions, I would love it if you can interpret what masterpiece you have built with the Lego and what do you think I have built with these two as well. So all three masterpieces.
Well, this is clearly a hippopotamus.
Right, clearly.
And this is a kangaroo.
Okay.
So you have the beginning of a zoo here.
Yeah.
This appears to be some sort of hybrid robot thing with an antenna.
Wow.
So I think it's a future zoo which contains some actual animals and some robotic creatures that inhabit the same zoo.
Fantastic. So relics of the past and then some future animals.
Right.
Yeah, which is the path we're heading down before the heat death of the universe. Amazing. Let's move into some of our closing questions. What are some books, movies, role models that have strongly influenced you in your life?
That's a good one. So I saw Stephen Hawking give a talk when I was an undergraduate. I found that very inspiring. He's an inspiring figure for many reasons. He was a great physicist, overcame this, incredible physical difficulty to survive for much longer than doctors thought he would. So I think, I always found him to be a very inspiring figure. I interacted with him over the years personally and a few times. But just the force of will and the degree of commitment to the interests he had intellectually, that's what inspires me more than anything. So people that are driven by something much larger than themselves, it's like, it's not about financial gain. It's not about anything immediately close to you. You're driven by something that goes way beyond yourself. You're driven by the desire to discover something new or to create something very innovative. I find that inspiring. I have that same urge. So people that I meet that are motivated by that sort of desire are the ones that I find the most inspiring. Mm-hmm. And there are some scientists who are able to really put that first and foremost. They're able to say, this is what I want to do with my life. I'm going to do the most interesting thing that anyone can do. And I'm going to push it forward as hard as I can. I may fail, but that's what I'm going to do. That's really admirable, I think. And I wish more people had that sort of motivation. I think, the great majority of us, understandably, focused on the difficulties of everyday life and sort of material success and, being comfortable that's all very understandable. But I find it inspiring when I meet people who don't have those motivations so much and who really are guided by something beyond that. Books and movies. I like 2001.
Classic.
Back in the day. It's a classic indeed. Yeah. And I think it's quite interesting at this moment because people are worried about AI and machines taking over. And that's a fear that goes way back and for good reason. For books, I read Hawking's A Brief History of Time when I was before I was in high school.
Yeah.
Couldn't understand anything. It's not an easy book to understand.
Yeah.
But it was inspiring. I also, my father is a theoretical physicist, retired now, but he showed me a demonstration of a superconductor, which you can make a magnet float above a superconductor and you can make it spin, push it around. So it's a form of levitation. And actually the coolest thing about that was you have to cool the superconductor down with liquid nitrogen. So liquid nitrogen, is that stuff you use in Halloween parties and so on. Yeah. Actually, it was more interesting in some way than the magnet levitating. But but that was just, how can this possibly work? It's something outside your ordinary experience. It looks like magic, but it's happening. So just that, I think that desire to go beyond our comfort zone, what we're used to, what we think is the way the world works, and discover something truly new. I don't have a lot of book suggestions really. I think Brian Greene's books are pretty good if you're interested in string theory. Lisa Randall has some good books. Yeah. Alex Valenkin has a good book about the multiverse. Mm-hmm. So those are some, but I haven't read that many of these sorts of popular science books actually.
Well, those great classics, good primers to read. If you were granted one wish, which is the biggest mystery in the universe, in nature, that you would like to solve, what is that one question that keeps you up at night?
That's a good question. I think I would want to know what came before the Big Bang, where the Big Bang came from, and what came before. Yeah, I think that's what I would want to know.
Yeah. Easy question.
Yes,
Pretty
absolutely.
casual.
Yeah.
You brought up Stephen Hawking and how some people chase something that's beyond money, fame, that you're chasing a bigger purpose. What would you like your legacy to be?
I'd like to discover something new that no one knew.
Mm-hmm.
And that's the main thing. I'd like it to be something interesting that, influences how people think into the future. And that's about it, really. I mean, obviously there's the personal side, family and so on. That's very important to me as well. But when it comes to research and work, it's to create something or discover something that was unknown before me, to make some sort of progress into the darkness that's around us on all sides and light up at least just a little bit of it.
Light up some of the darkness around us. We started the interview talking about how you view your work, and you brought this up as well. And now you mentioned lighting up the darkness. We are floating around this big question around purpose. So let's tackle that as a final question. In the book Cat's Cradle by Kurt Vonnegut, there's the following words. In the beginning, God created earth, and he looked upon it in his cosmic loneliness. And God said, let us make living creatures out of mud, so the mud can see what we have done. So God created every living creature that now moves, and one was man. Man sat up and spoke. What is the purpose of all this? He asked politely. Everything must have a purpose, asked God. Certainly, said man. Then I'll leave it to you to think of one for all of this, said God. My question for you, Matthew Kleban, final question. What is the purpose of all of this? What is the meaning of life?
42.
Yeah.
What is the purpose of all this? Yes. I mean, I hate to say it, but I agree with God in that quote. I don't know that there needs to be a purpose.
Okay.
I think life exists possibly because of the arrow of time that you mentioned, that if you start from a low entropy state, complexity can come into being and will come into being inevitably as entropy increases. So life will form, it will evolve, it will become self-aware, it will think, it will ask these questions. I'm not sure that there has to be a purpose there. It might be part of a giant cycle that goes on forever. It might be, I don't know how it began. I think that is a very deep question to which we don't have a good answer. But I think it's not clear that there is a purpose. All I can say is we are where we are, and I don't think there's anything more valuable or interesting than asking questions like that, trying to dig into it and figure out what we can figure out. Right, we have our moment now, so we shouldn't let it slip away. We should dig down. We should understand as much as we can. We should put all of our effort into that. And I think there's an important message, and I think you're conveying it with this series of podcasts you're doing. You're asking people really interesting and hard questions. That's great, because again, so much of what people do, so much of what people think about is focused on the material world, their immediate circumstances, their dinner that evening, whatever. And it's totally understandable. Not saying there's anything wrong with that. But that really shouldn't be why we're here, if there's a purpose. And even if there isn't, it shouldn't be what we're focusing on. We as a species have the luxury to be able to sit down and ask questions like this. We don't have to be out hunting and gathering all the time. We're not fighting for our survival. We have the luxury to think these kind of thoughts. We should take advantage of it. We should spend our extra effort on questions like that, or creating beautiful works of art, or doing things, helping people who are in need, but things that have a meaning beyond ourselves. So if there's a purpose, I think it's that.
So locally, ask questions, create things beyond yourself. Globally, there is no purpose. I love it.
Okay.
Professor, thank you so much. If people want to connect with you, find out more about you or your work, where can they do so?
They could go to my website, send me an email. The email is on NYU's website. That's about it. I don't use social media. So
yeah, that's the place to find you. Professor, thank you so much for a fantastic conversation. It was an honor.
Thank you very much, Shalaj. I appreciate it.